In the first question here, we want to write the electron configuration for each of the following atoms and ions. So looking at sodium, sodium has a total of 11 protons, which means that it also has 11 electrons because we have a neutral atom of sodium here. So those 11 electrons need to be distributed into their energy levels and their shells, S, P, D, and F. So over here in green, I have the S block. In purple, this is the P block. Blue, this is the D block. And in red, that is the F block. So looking at sodium, we're always going to start with hydrogen. So hydrogen would be 1s1. Helium is going to be 1s2. So every time we get to the end of a section, we want to write down the configuration we've achieved so far. So I've placed 2 out of the 11 electrons. So now I'm going to come down over to lithium. Lithium is going to be 2s1. Beryllium will be 2s2. So that's 4 total electrons. Next, I'm going to come across to the P block here. So this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So that's 10 electrons. So now I'm going to come down one more row, and now I'm at sodium. So that's going to be 3s1. So if we count the total number of electrons, 2 plus 2 plus 6 plus 1, we get a total of 11 electrons. Looking at the next one is an ion. This is calcium plus 2. So that plus 2 is telling me that calcium has lost 2 of its electrons. And it's going to lose those electrons that are the furthest away from the nucleus, the ones that are in the valence shell. So I'm going to go ahead and do my configuration for calcium. So down here to 3s2, come across, this is 3p6. And then normally I would have 4s2, but since this is calcium plus 2, we've actually lost those 2 valence electrons. Phosphorus has a total of 15 valence electrons here. So that configuration will be 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3. And then the last one that we have here is chlorine minus 1. So normally chlorine has 17 electrons when it's neutral, but since this is chlorine minus 1, this means it's gained an electron. So whenever I write out my electron configuration, this is the normal configuration here, 3p5. But since we have a minus 1 charge, this becomes 3p6. So whenever we look at the number of valence electrons that are present in each shell, my valence shell is the highest energy level. Now sometimes that's split between S and P, so make sure you include both of those. But when we look at the number of valence electrons here, sodium has 1 valence electron. Calcium plus 2 has 8 valence electrons. Phosphorus has 5 valence electrons. And chloride here is going to have 8 valence electrons. So calcium and chloride here have a full octet because they've gained or lost electrons to get to that octet. In the next question, we want to rank these from highest to lowest. So there's 2 things that we have to think about here whenever we're dealing with these periodic trends. So first we need to think about shielding, which is related to the layers of electrons, the energy levels. And then we need to worry about nuclear charge, which is basically just how positive is the nucleus. So let's start with electronegativity here. Electronegativity is how strongly an atom is going to attract electrons that are in a bond here. So when we look at our choices here, we have O, F, S, and Cl. So what's going to be attractive to an electron? Electrons are negative, so they're attracted to positive nuclei. And the closer that they can get to the nuclei, the more strong that interaction is going to be, the more attractive it's going to be. So looking at O and F versus S and Cl, O and F are going to have 2 layers of electrons, whereas S and Cl are going to have 3 layers of electrons. So 3 layers means that those electrons are farther from the nucleus. So we can eliminate the 3-layer atoms because that's going to be less attractive than 2 layers. So then between O and F, they both have two layers, meaning that shielding is constant. So the thing that's different about O and F is the charge on the nucleus. The nuclear charge in F is +9, whereas in oxygen, it's only +8. So the highest electronegativity then is going to be F. The next highest would be oxygen. And then between sulfur and chlorine, they both have the same layers, but chlorine is more positive. So its nucleus is going to be more electronegative, more attractive to electrons. So we end up with chlorine and then sulfur. The next one we have is ionization energy. So this is a measure of how much energy we need to take away an electron. If the electron is really strongly attracted to its nucleus, it's going to be difficult to remove it, and we're going to need a high amount of ionization energy. So the ones that we're looking at here, we're looking at C, N, Si, and P. So we've got some of them that have 2 layers and some that have 3. So it's going to be easier to take an electron away that's in the 3rd energy level than in the 2nd, because the 3rd energy level is farther away from the nucleus. So we know that the highest ionization energy is going to be either carbon or nitrogen, and it's going to be nitrogen first because its nucleus is +7, then carbon, which has a +6 nucleus. So yes, silicon and phosphorus do have more protons. They're 14 and 15 protons, but they also have 1 more layer of electrons. So between silicon and phosphorus, phosphorus is going to have a higher ionization energy because its nucleus is more positive, and then the lowest would be silicon. So the last one here is atomic radius. So this is just the size of the atom from the center of the nucleus to the edge of the electron cloud. And we are looking at these 4, Na, Mg, K, and Ca. So first let's think about the shielding, the layers of electrons. Sodium and magnesium are both going to have 3, whereas potassium and calcium will have 4. So we already know that potassium and calcium are going to be bigger than sodium or magnesium because they have 4 layers of electrons. So between potassium and calcium, which one is going to be bigger? Calcium only has 19 protons in its nucleus, whereas calcium has 20. So potassium is going to be a little bit larger because its electrons are not so strongly attracted to the nucleus as in calcium. So potassium, calcium, then between sodium and magnesium, sodium will be larger because it has only 11 protons, so the attraction is weaker and the electrons are not as close. And then the smallest atomic radius here would be magnesium. So we want to use shielding to explain why the radius of rubidium is bigger than the radius of potassium. So here we have a potassium atom and a rubidium atom. So the difference between these two is going to be the number of layers of electrons. So potassium only has 1, 2, 3 layers of electrons here, whereas rubidium has 1, 2, 3, 4 layers of electrons here. So because of the fact that rubidium has more energy levels, we know that its radius is going to be bigger. So then how does that relate to shielding? So if we had an electron that was in this outermost energy level, all of the electrons that are in the first, second, and third energy levels, those are all blocking this electron from the nucleus. It's kind of like you're at a concert and you're in the fourth row and there's 3 rows of people blocking your view of the stage. So because of that, the attraction is weaker between those valence electrons and the nucleus. There's all this shielding blocking those electrons from the nucleus. So this shielding makes the attraction between the valence electron and the nucleus a little bit weaker, which makes the radius just a little bit larger. So shielding blocks outer electrons from the nucleus. This causes a weaker attraction because we have a greater distance. So when that attraction is going to be weaker, the radius gets larger. The electrons are not being held as close to the nucleus, so we're getting that larger radius because of the weaker attraction. So this applies whenever we're talking about a column, especially because each of those elements in that column has an additional layer of electrons, so the shielding effect becomes stronger as you move from the top of a column down to the bottom. Next, we want to use nuclear charge to explain why the radius of carbon is larger than the radius of nitrogen. So both of these have the same amount of shielding. They both have 2 layers of electrons here. So shielding is constant between carbon and nitrogen because they're in the same row. They're in the same period on the table of elements. So then what's difference here? Well, in one, we have a +6 nucleus and a +7 nucleus. So my +6 nucleus has a lower nuclear charge. This means that these electrons are going to be not quite so closely held to the nucleus. Because it is a +6, which is a little bit less than +7, the electrons aren't as strongly attracted. So because we have that weaker attraction, that gives us a larger radius. Those electrons are not held as close to the nucleus in +6 in carbon than it would be with a +7 nucleus in nitrogen. So what column corresponds to the following groups of elements? So our halogens are going to be column 17 here. So this includes fluorine, chlorine, bromine. All of those are considered halogens. Noble gases are found in column 18, which is the farthest right on the periodic table. All of these elements have a full valence shell, which means that they're very non-reactive. They already have the correct number of electrons in their valence shell. So for helium, that's only 2, but for everybody else, it's going to be 8. Helium only has 1s electrons, so 2 is considered a full valence shell for helium. Alkaline earth metals and alkali metals. So alkali metals are column 1 and alkaline earth metals are column 2. So these all either have 1 valence electron or 2 valence electrons. So they have very similar chemical properties. Anything that's in the same column will have very similar chemical properties because they have the same number of valence electrons. In question 6, we want to write the electron configuration for sulfur 33. So a little bit information about the way that that's written. Sulfur 33 is indicating to you that this particular atom of sulfur has a mass number of 33. So that's the sum of protons and neutrons here. So sulfur has 16 protons, which means that it must have 17 neutrons based on the mass here, the mass number here. So this is a neutral atom of sulfur, which means it's going to have 16 electrons to match those 16 protons. So my electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So this means that I have a total of 6 valence electrons here. So this is important because, again, those valence electrons are going to dictate the chemical properties. So sulfur has very similar reactivity to oxygen because they share a column and they have 6 valence electrons. So we want to draw a Bohr model of the atom, including labels for the number of protons, neutrons, and electrons in each energy level. So I know from my configuration that I have 3 energy levels. My first energy level has 2 electrons in it. That's my 1s2 energy level. My next energy level has a total of 8 electrons. 2 of them are in S and 6 of them are in P. So I'm just going to draw my 8 electrons. So 1, 2, 3, 4, 5, 6, 7, one more makes 8. And then my highest energy level, which is my 3s2, 3p4, has a total of 6 electrons. There's 1, 2, 3, 4, 5, and 6. So whenever we're talking about this particular atom here, my nucleus is going to have those 16 protons and 17 neutrons in it. And each of my energy levels, we're going to have 2, 8, and my valence shell has 6. So the number of valence electrons that we have is 6 valence electrons. In question 7 here, we want to identify the unknown element here by matching its spectrum to these elemental spectrums. So what we're doing here is we're basically trying to match the lines. So in order for any of these elements to be present in the unknown, all of those lines must be present. So sometimes we have a mixture where we have 2 different elements present in the unknown. Again, we just want to match up the lines to figure out which elements are present in the mixture. Now, in this sample, we can see that our spectra here doesn't quite match manganese. It doesn't quite match beryllium, but it does match strontium here with this purple line. Then we have these 3 emissions in the blue region. We've got a red-orange and then some red emissions as well. So because this matches completely, we know that the unknown is going to contain this strontium. So this is the spectrum of light that is emitted whenever these different elements are exposed to some energy. So the electrons within the different energy levels of these atoms absorb that energy and become excited. That excited state is unstable, so they re-emit that energy to jump back down to what's called the ground state. The ground state doesn't have to be the lowest energy level. Like the ground state is not always energy level 1. It's whatever the normal state, the normal energy level that electron is found in. So when they give off that energy for the electrons to jump down in energy level, that gives off characteristic wavelengths of light based on how much of an energy jump the electrons are making. In question 8 here, we want to complete the table below about atomic structure. So in the first one, we're given the symbol here. So the bottom number is going to be the atomic number. So that's going to be 15, which is the same as the number of protons. We also know that the charge is 0 here. So we must have equal numbers of protons and electrons for that to be true. So then to figure out the mass number, that's given as 31 in the symbol here. That's the number that's on top. So that mass number is the sum of protons plus neutrons. So I know that I have 15 protons, which means I must have 16 neutrons. So the name of this would be phosphorus 31. In the next one, we have chlorine 36. So my mass number here is 36. The atomic number for chlorine is going to be 17, which means 17 protons. Since the charge here is -1, I know that I have one more electron than proton. So my charge is really going to be my protons minus my electrons. So then to figure out the number of neutrons here, my mass number is 36, and I know that 17 of that 36 are protons. So that means that I have 19 neutrons here, because 19 plus 17 is going to give us 36. So whenever I go to write the symbol here, I need the atomic number on bottom, the mass number on top, the element symbol, and then since this one has a charge, I'm going to put -1 here. Question 9, we want to describe how to find the average atomic mass given the abundances and masses of several isotopes. So our first step is going to be to convert our percent abundances into decimals. Basically, what we're doing here is we're just going to divide by 100. Once I've done that, my second step is going to be to multiply each decimal abundance by the mass of the isotope. And then once we've done all of that multiplication for each isotope, so you'll be given the abundances and masses, you multiply the decimal abundance times the mass for all of the isotopes. So if you had 5 isotopes, you would do this for all 5. And then lastly, your final step would be to add up the products. So whatever I got from multiplying the decimal abundance by the mass for however many isotopes are present, I'm going to do that and just add up all of those values to get my average atomic mass. Now, one of the things that students often do whenever they do this problem, is that they'll give me an average rather than a weighted average. So a weighted average is taken into account the fact that they have different abundances. A regular average assumes that everything has the same abundance. So if you had 3 isotopes, you're not going to add up those masses and divide by 3. That makes the assumption that all of those isotopes are equally abundant, when in fact it might be that isotope A is 80% abundant and B and C are 10% abundant each. So that would mean that the average should be closer to isotope A than it is to isotope B and C. So in question 10 here, we are looking at a hydrogen atom. And this is showing us the visible light transitions in the hydrogen atom. So some of these transitions might be too large and might produce wavelengths that human eyes can't see. Some transitions might be too small and it produces infrared wavelengths that human eyes can't see. So for your eyes to be able to see the light given off in this electron transition, it kind of needs to be a Goldilocks amount of energy that your eyes are able to see. So when electrons move between energy levels, so what's going to happen first is that the electron is going to absorb energy. So this could be, say, from the heat and energy that's supplied by a Bunsen burner, or it could be that some X-rays or some ultraviolet radiation is shined on some atoms, and then those electrons absorb that energy. But the electrons are going to absorb energy, and this causes them to move up in energy level to what we call the excited state. Now, the excited state is just a higher energy level than that electron would normally be in. So, for example, whenever we think about hydrogen, it only has 1 electron, and that's in the first energy level. If the electron is in any other energy level, we would call it an excited electron, an excited state. So this excited state is unstable. So because this excited state is unstable here, this means that those electrons are going to re-emit the energy they absorbed. And then this allows them to move down in energy level. This is what we call the ground state. Now, the ground state doesn't have to be the first energy level. So, for example, if we look at something like carbon, carbon's electron configuration is 1s2, 2s2, 2p6. So if that, or rather 2p2 rather, not 2p6, if that electron is in its 2p orbital, that's its normal state. That's its ground state. Perhaps it jumps up to the 5th energy level. It would re-emit that energy to get back to that 2nd energy level. So we want to convert the wavelength of the photon of light that was given off during this transition. So the electron is relaxing from the 2nd energy level down to the 1st energy level. It releases a photon of light with a wavelength of 656 nanometers. So we want to convert this nanometer into meter. So that means nanometers needs to go on bottom so that unit cancels, and meters needs to go on top. So 1 meter is the same thing as 1 times 10 to the negative 9 nanometers. You could also write it, 10 to the positive 9 here. You could also write it like this. So 1 meter is 1 times 10 to the 9 nanometers, or I could write it like this. 1 times 10 to the negative 9 meters is the same as 1 nanometer. So either conversion factor, they're both the same. Just make sure you put the correct number in the correct place. So when I solve this, I get 6.56 times 10 to the negative 7 meters. So why do we need to do this? In the next couple of questions, we're asked for the frequency and the energy. So we want to make sure that whenever I plug in my wavelength into those wave equations, that my units are all going to cancel. So I need to make sure my wavelength is in meters instead of nanometers. In the next question, we're looking for the frequency and then the energy of this photon. So we're going to use our wave equations, which I've included up here. So first we have V is equal to F times wavelength. So if I want to solve for frequency, I need to divide both sides by lambda, by wavelength, so that I isolate the frequency term. So here we have V over wavelength. Now we're talking about a photon of light. So that tells me that this is the speed of light, which is 3 times 10 to the 8 meters per second. We want to divide this by the wavelength, which we've previously converted into meters here. So that's 6.56 times 10 to the negative 7 meters. We needed that to be in meters because we want for meters per second and meters to cancel out, leaving us with units of per second, s to the minus 1. You could also write this like this, 1 over second. Both of those are the same. So when I do this division here, we want to be careful to make sure that we're typing this in our calculator properly. So using your parentheses around each number to make sure that our calculator does the correct order of operations, I get 4.57 times 10 to the 14 for my frequency here. Now that we've found our frequency, we can now calculate energy. So energy is equal to H times F. So H is just a constant. It's called Planck's constant. It is 6.626 times 10 to the negative 34, and the units here are joules times seconds. So when we multiply by our frequency, which we just calculated in the last problem, notice that units of seconds are now going to cancel. So then the only unit left will be joules, which makes sense because we're solving for energy here. So again, using parentheses around these numbers in your calculator, we're going to get our answer of 3.03 times 10 to the negative 19 joules.